Hello, welcome back to the shrine. Today we are going to give a spa treatment to my phase converter. This unit generates the 3-phase voltage for all the hand-me-downs in the shrine. It's been super noisy at times, but recently it started to switch to a real annoying pitch occasionally. First thing is to shut off the breaker. So there's a 30 amp breaker. So this will not start. I bought this unit used and they populated some switches here. I just covered it with tape. It had some extra capacitors, I guess for boost, because the guy's power system wasn't able to run the motor. Anyways, I got rid of those extra caps and then I get rid of the switches here. That's why this is covered off. So the whole thing just comes off like so. You can see the magic inside. I'm just gonna go and make sure there's no power in the system. So this black wire and the white wire, those are the two lines that coming in. This is the 3-phase that's going out. You can see that the black and the white wire is basically the same bus as those, and then the system generates the 3rd phase with the red wire. What I'm gonna do is disconnect the load motor from this box. So it's not under power. Now the load motor is disconnected, I can just safely move it to the table. First thing is to pop this cover off. Curious to see what's in there. Well, not much. Just a lot of dust and some cables. It doesn't even have a terminal assembly, as you can see. It's just the cables directly wired to the outlet cables. I want to replace these cables anyways. These are 10 wire gauge. I want to have some kind of metal shielding around it. Never taken apart a motor like this. Usually the motors that I worked on, they always have a shaft coming out one end or the other, or both ends. I have a feeling that this motor had a tough life. You know, these motors are turned on, run there all day, and people usually forget about them. So they can collect a high amount of cycles, and then sometimes they go up in flames by the time someone figures it out. Just gonna use a brass punch to loosen the cover. I thought it's gonna fight me, but it didn't. The bearing looks well lubricated, and there's grease, and then there is this metal grate on it. I think it was added to prevent some critters going inside. You can hear that tone. Maybe that's where the sound is coming from. It definitely has a similar sound to this one, the annoyance sound. Let's try to take out the rotor. Something tells me it goes out to the other side. Take out the bolts. These are just long through bolts. Covers off. And this has a different color grease in it. The previous one was brown, this is greenish. And it's got the same grates on it. You can see it's only being held by these 4 bolts. And there's the sound. I think that's the source of the annoying sound. I'm just gonna mark these, make sure everything goes back in the same position. That's why the rotor didn't come out that way, because there's the fan. So let's try it this way. There you go. Everything seems to be in a good order, except that bearing here. So if I roll this bearing, you can hear that special bearing sound, especially if it's laying down like this. I think this bearing is toast. I'm gonna need to go and replace it. So there's a lot of debris inside here. I'm not sure what this is, if it's fret wear, some kind of dust just collected here. The stator looks to be good. The wires are solid. They are not moving around, so there's not much else that can make the annoying sound. I didn't find anything wrong with the stator. It's just a standard stator, distributed winding. The coils are not discolored. I was looking for these welds. If the welds here are broken, the yoke can move relative to the foot, but all these welds look good. Same on the other side. So there's no cracking, there's no rusting along the welds. Everything checks out. One more thing, I wanted to check if this cover moves relative to the housing, but it's all good. There's no discoloration on this side, on the welds. Everything is solid, everything is varnished. So the next thing, we're gonna pull the bearings off. This is the fan end of the rotor, and you can see it's got a bearing on it. Then here's the cover, and you can see the grease inside the cover. Also, there's a grease fitting here. So if you want to add grease, you just hook it up here and then pump it in. And what does that grease do? Well, not much, because you can see it's a shielded bearing. There's no way this grease, when it's pumped in, it will go through that little gap here in the shield and then essentially go inside the bearing. This should have been an open bearing, not a shielded one. At least open on this side. So you can see the grease there. It's the same story on both sides. Can you hear that? That bearing is not good. That's why this motor is whining so low. Let's see how much fight this is gonna put up. Not much. And it's off. Let's see if this is gonna put up a fight. Looks like it's not. Just slowly sliding off. These are both 6205Z, and it says Poland PPL. So some kind of cheap bearing. It doesn't really have a manufacturer like SKF or NSK. And interestingly, when I flip it over, I can feel the inner race inside is loose. There you go. Let's check this one. They both have grease inside, but the grease is kind of congealed. The outside diameter is 52, the inside is 25, and it is 15 millimeter wide. I was ready to fire up Amazon, see if they can bring me some bearings tomorrow, but look what I found. Absolutely unrelated. Some old bearings just laying around, and don't ask me where from. I have no idea. They've been in the drawer for probably 20 years at least. 6205L8, and it's made by NTN. Now NTN is a Japanese bearing maker, so anytime you replace one bearing to an NTN one, I guarantee you it will work better than the original bearing. So these are the same part number, so the size should be the same. You can see it's 52 by 25 by 15. So I'm just gonna go and assemble these. They got double seal, so they sealed for life. You know, these have the shields. These are just metal shields, but you can pump the grease in 24/7 when the shields are on. It's not gonna get to the rolling elements. Don't tell me that. Just gonna go and persuade this bearing onto the shaft. Just like that. Here's the other side. Should be good, but it can always be better. There you go. Now it's seated. Let's double check this side. Done. Now the rotor can be assembled back, just like that. Good. I'm just gonna go and factory delete these meshes. I'm pretty sure the good people at Gentech, you know, put this in to prevent critters from going in, but all it does just creates this really annoying noise. So I'm done with it. No more noise. Now the cover can go back. Next are the through bolts. And then the other cover. There's no marking on it, so I'm just using the grease fitting and then the center line of this box to orient it. Finally, these nuts can be assembled. I've been getting ready for this for 2 years. And this noise was just so annoying, I cannot tell you. But I could never shut it down because I need the machinery to run, the lathe, the mill. But no, it's over. And finally, I can have my peace in the shrine for the hand-me-downs of the industry. The rotor turns freely, so that's positive. So one of the reasons this was super annoying, because it was not mounted down to a stable platform, and it was able to dance around just on the floor. I never had the time to properly set this up. So I have a lot better idea than that. These are different size isolation mounts. This is M10 size, so hopefully it will be able to go through that hole. And I'm gonna build a platform and utilize these and essentially hook it up to some heavy-duty machinery so it will not be able to dance around. Next item on the list is to put all these cables into a neat package like this one, so that it's safe, there's no fretting of the wires. So I got all the hardware for it. I'm just gonna go and trim this conduit to size and essentially fish the wires through. And just like that, it's packaged into a neat package. This conduit is real great. It's a flexible conduit and it's cut to size. I've got about 8 to 10 inches of free wire on the other end. Now the idler motor is mounted on this sturdy steel frame. This frame was a small lathe base in its previous life. I repurposed it. Now I use it to hold my arbor press and some of the grinders. This is as heavy duty as it gets. I was drilling these holes. I think the thickness was in the range of 3-4 millimeters. I drilled and tapped the M8 threaded holes here, and then I tried 2 different dampers. I think these taller, skinnier ones, they will give a better performance. So now all it's left is just bolted down to the base. I am using these self-locking M10 nuts. They are stainless. So hopefully this is the last time I have to deal with it. So I got the idler motor cables connected back. It's time to switch it back on. And do a test. I gotta say it's a lot quieter than it was in the past. It was really annoying. I might go and add some panels here with sound dampening and see how it's gonna turn out. But it's not rocking, it's not moving, it's not going anywhere. The next thing we need to do is to measure the voltages in a box and make sure that it's balanced. We're gonna go and measure volts AC. I got the voltmeter hooked up to 2 of the phases. I'm going to turn it back on. Now I got it connected to the other phase. Here's the third one. 254.5. So this is what the voltages look like. You can see that there's an imbalance. So 248, 242, 254. So in this case, what we might want to do is swap two of the wires from the idler motor and test it again. Considering all the variations, I'm gonna go and switch back to this setup here, which results the lowest amount of voltage between the high and the low. So you can see it's 12.5 volts. These both result 14.3, 14.4 volts. So I'm going to switch back to this one. The last thing I want to do is install this kit for the phase converter. And it's got a display which will be able to measure the voltage and the current. There's a current sensor here. And it's really easy to install. There's a diagram on the back. You can see that we got the voltage coming in here. So we can put the ferrite ring around one of the lines and then hook up the other lines to two of the wires. So this is 80 to 260 volts, 50-60 hertz. The size of this box is 45 by 85 millimeters. So I took the original cover from Gentech, and there were two switches here, two buttons that was switching some extra capacitors. So I'm just gonna go and increase the size. So hopefully this will fit through and it will be like a seamless implementation. And just like that, it's installed. Time to put it back together. Here's the box. You can see two wires go to the inductive current sensor here. So I just put it on line 2 that goes out, and then the voltage that goes to the box is connected to line 1 and 2. So I'm going to be measuring the voltage between those two lines. So let's go and switch it on, see how it works. It's upside down. So much about the label. See, the label is facing right way up, the text is up, but the box is upside down. Trust nobody. Well, the phase converter is not much quieter. Hopefully it will not change the pitch and go into super annoying mode. The Gentech front end is pimped up with this new display. You can see it's pretty cool. Let me get you closer. So here it shows the voltage. It is consuming 28.8 watts, 60 hertz frequency, 0.34 power factor. Power stations probably hate me. And it is drawing 0.345 amps of current. So that's just enough to get the idle motor running. So now I'm gonna go and turn on the lathe. It's consuming about 8 amps. I'm gonna switch the lathe to 1200 RPM. And it's consuming 8.4 amps. Now I'm gonna turn on the CNC. So the CNC is on. You can see it's only drawing 1 amp. Obviously the motor is not running, it's not cutting metal. so it's only the onboard computer. So here's a waveform that I recorded with the Rigol. And you can only see two phases here because you know, the peak-to-peak voltage for this three-phase system can be like 600 volts. So I had to use special probes, and I only had two probes to record this. You know, this is a 4-channel oscilloscope, so it would be able to record more, but again, I only had two probes. So here's another recording that shows the normal waveform, and then when I turn on the lathe, you can see that the waveform is gonna shrink. Basically, when the lathe motor is turning on, it's gonna act as a big inductance, and it's gonna clamp the voltage down from its nominal, I don't know, 240 volts to maybe 200 volts, maybe 280 volts. You can see that the waveforms are in a proper position relative to each other as far as phase, so they are 120 degrees apart. And with that calming idle motor sound, I'm gonna sign off. So this is gonna be a wrap. I appreciate your time. I hope you enjoyed the video and maybe learned something. If you like the video, please give me a thumbs up, leave a comment. If you want to see what I work on next, please don't forget to subscribe. See you next time. Bye.